Welcome back. In this lecture video, we're going to be looking at the specific details for inference procedures for population means and population proportions for IID random sampling. Now you'll recall that IID stands for independent and identically distributed, and IID random sampling is the type of sampling procedure that you would have used in your first methods course, which is the prerequisite for this course. All right, and so IID random sampling occurs if you are sampling from an infinite population, or if you are sampling from a finite population, you are sampling with replacement. So either of those two scenarios involve IID random sampling, and we're going to be looking at procedures that are appropriate for that type of sampling procedure. Now let's review inference procedures for a population mean first. The three types of hypotheses that can be tested are given below, with the specific details for carrying them out on the subsequent slides. And so you'll recall from your first methods class that there are three types of hypotheses that we can test: the two-tailed test, the left-tailed test, and the right-tailed test. Now, the two-tailed test has a null hypothesis that says that the population mean, mu, is equal to some hypothesized value, which notationally I will represent by mu sub 0, versus the alternative hypothesis, which is, again, the opposite of the null. And the opposite of the null in this case would be that the population mean is not equal to that pre-specified or hypothesized value. The left-tailed test has a null hypothesis that says that the population mean mu is greater than or equal to some specified value, against the alternative hypothesis that says that the population mean mu is less than that specified value. And then finally, we have the right-tailed test. The null hypothesis for the right-tailed test says that the population mean is less than or equal to some specified value, mu sub 0, against the alternative hypothesis that says that the population mean mu is greater than this hypothesized value. Now, you'll recall that one way of knowing how to set up your hypotheses is that what the researcher is trying to prove or conclude is what goes in the alternative hypothesis. And so, for example, if the purpose is to try to show that the mean of a population is less than a particular value, then that would correspond to the alternative hypothesis of the left-tailed test, and so the left-tailed test would be used. If the goal is to show that the mean of a population exceeds some value, then that would correspond to the alternative hypothesis of the right-tailed test, and so the right-tailed test would be used. All right, and if an underlying assumption is that the mean of a population is equal to some value, all right, which would be the assumption for the null hypothesis, and it's the goal to try to detect when that's not the case, then that would correspond to the alternative hypothesis in the two-tailed test, and so the two-tailed test would be used. So these three types of tests exhaust the possibilities, and it's very flexible. We can answer many kinds of questions with these three hypotheses. All right, now the test statistic, and I'm going to be using the standardized test statistic, which we discussed in a previous lecture video. One could use an unstandardized test statistic or a standardized test statistic. In general, I think that the unstandardized test statistic is good for teaching purposes, but when you become familiar with hypothesis testing, when you're comfortable with that, you understand it, and you're then trying to do it, then I think that the standardized test statistic becomes more convenient to use. And so, and by the way, we are looking right now at this situation where we're assuming that the population standard deviation is known. Now, that may be a little bit unrealistic, but we're going to start here as kind of an easy entree into this, and then we will generalize and look at the more realistic scenario where the population standard deviation is not known. All right, but for now we will assume that the population standard deviation is known. And so in that case, the test statistic, the standardized test statistic for the test is given by this expression, the sample mean minus the hypothesized value, the value that shows up in the hypothesis, and then we divide that difference by sigma sub x bar. Now that is the true standard error of x bar. All right, and so this is the notation that I'll use to represent the standard error of x bar. And we can also describe this as the standard deviation of the sampling distribution of x bar. All right, but it's a little bit easier to say standard error of x bar, and so that's typically what I will use. All right, so that is the standardized test statistic that we'll be using, and we're going to call this zcalc. All right, and we will explain why in a moment. Now, what is this zcalc measuring? What is the interpretation that we can attach to it? Well, zcalc is the number of standard errors that x bar, the sample mean, is from the standardized value, or I'm sorry, the hypothesized value of the population mean mu sub 0. So the numerator is the deviation from, we can think of it as a distance, but it's a signed distance, okay, that x bar is from the hypothesized value of the mean. And the units of that signed distance would be the same as the units of the data. All right, but we then divide that signed distance by the standard error of the sample mean x bar, and so then it becomes a measure of the number of standard errors of x bar that x bar is from a hypothesized value of the population mean. So it's a way of measuring how far x bar is from the hypothesized value of the mean in terms of standard errors. Now, in order to use this test statistic to make an inference, to draw a conclusion about which of the two hypotheses we think correspond to the true state of nature, we need to understand how zcalc behaves. We need to understand its probabilistic behavior, and we need to know this because we need to identify values of zcalc that would be inconsistent with the null hypothesis. All right, and then once we know that, then we can come up with rejection criteria. So we need to understand the probabilistic behavior of zcalc under both the null and alternative hypotheses, but primarily in terms of setting up the test and determining the rejection criteria, we need to understand the probabilistic behavior of zcalc under the null hypothesis. All right, and so we know that if the null hypothesis is true, then the mean of the sampling distribution of zcalc will be 0, and if the alternative hypothesis is true, then the mean of the sampling distribution of zcalc will be non-zero. It will be something else different from 0, and in particular, it will be equal to mu minus mu naught over the standard error of x bar. And in either case, regardless of whether the null hypothesis is true, the standard deviation of the sampling distribution of zcalc would be 1. All right, so that tells us a little bit of information about the sampling distribution of zcalc, both under the null hypothesis and under the alternative hypothesis. But we also need to know something about the shape of the distribution, and the more information that we can get regarding the sampling distribution of z-calc, the better. And so we know that if the population that we're sampling from is a normally distributed population, then the sampling distribution of z-calc will be a normal distribution. That's what this is saying here. So if we're sampling from a normal distribution, then z-calc will also be normally distributed. All right. If the population that we're sampling from is not exactly normally distributed, then z-calc will not be exactly normal. However, if we have a large sample, a sufficiently large sample, then the sampling distribution of z-calc would be approximately normally distributed. All right, so that gives us a lot of information about the probabilistic behavior of the test statistic z-calc. All right, and so we know for a fact that regardless of the shape of the distribution, we know that if the null hypothesis is true, the mean of its sampling distribution is 0. If the alternative hypothesis is true, we know that the mean of the sampling distribution of z-calc is non-zero, and in particular, it's given by that expression there. We know that in either case, whether the null hypothesis is true or the alternative, we know that the standard deviation of the sampling distribution of z-calc is 1. And then finally, the shape of the sampling distribution of z-calc will be exactly normally distributed if the underlying population is normal, and it will be approximately normal if, regardless of the shape of the population we're sampling from, if we have a sufficiently large sample size. Now, in making inferences about a population mean using the sample mean, sufficiently large can be as small as n equal to 30. Many studies have shown that even for highly skewed distributions, if you've got 30 observations from that population, from that skewed distribution, the sampling distribution of the sample mean is bell-shaped. It will still have a little, some skewness, but it won't have much skewness. And the sampling distribution of the sample mean, even in those kinds of situations, is well approximated by a normal distribution. All right, so a sample size of 30 is the typical rule of thumb for sufficiently large when we're talking about testing hypotheses about a population mean or constructing confidence intervals for a population mean. Okay, so because we know that the sampling distribution of z-calc will be at least approximately normally distributed, then the standard normal distribution, which is the sampling distribution of z-calc if the null hypothesis is true, the standard normal distribution is the reference distribution from which we get the critical points for the 3 tests that we're looking at here. And so for the two-sided test, all right, which again is hypothesis A, then we would reject the null hypothesis if z-calc is either really small or if it's really big. Well, how small and how big does it have to be? Well, if z-calc is less than negative z sub alpha over 2, or if z-calc is greater than positive z sub alpha over 2. And remember that alpha is the significance level that we're using for the test. Now, if we are performing a left-tailed test, then we are going to reject for small values of our test statistic, and in particular, if z-calc is less than negative z sub alpha. And then finally, if we're performing the right-tailed test, then we're going to reject the null hypothesis if z-calc is greater than positive z sub alpha. And you'll recall that z sub alpha is the upper alpha percentage point of the standard normal distribution. In other words, z sub alpha is the number on the number line that gives us, or such that the area under the standard normal curve to the right of that point is equal to alpha. And this is the probabilistic statement for that. The probability, z sub alpha is the number on the number line, such that the probability that z is greater than z sub alpha is what's in the subscript there, alpha. Okay? And also where z, remember this is the standard normal random variable. All right, and then we can also calculate a p-value for each of these three types of tests. So we could, in determining or in drawing a conclusion based on the data, we can use the test statistic method, where you would calculate the test statistic and then compare it to our rejection criteria. We can also use or calculate a p-value and then compare that p-value to the significance level that we're using for the test. So you can use either of those two approaches. You typically would not use both. You would either use the test statistic method with the rejection criteria, or you would use the p-value method. Okay, so let's see how to calculate the p-value for these three tests. And again, these formulas assume that we're using the standardized test statistic. So for the two-tailed test, we are going to, the p-value is equal to 2 times the probability that the standard normal random variable z is greater than or equal to the absolute value of the test statistic. All right. For the left-tailed test, we're going to reject the null hypothesis. I'm sorry, the p-value calculation. The p-value for this test is the probability that the standard normal random variable is less than or equal to the observed value of the test statistic z-calc. So, and by the way, in these formulas here, the lowercase z-calc is the observed value of z-calc. All right. And finally, for the right-tailed test, the p-value is equal to the probability that the standard normal random variable is greater than or equal to z-calc. So, and by the way, I would just point out that in the p-value formula for the two-tailed test, we're taking the absolute value of z-calc, but we're not taking the absolute value in either the formula for the left-tailed p-value or the right-tailed p-value. And you'll recall that the formula, or the definition of the p-value is that it's the probability of observing a value of the test statistic at least as extreme as that which has been observed under the assumption or given that the null hypothesis is true. And so that is the reason for these formulas. Okay. Now, we can also calculate a confidence interval for the population mean, and in some cases we would construct a two-sided confidence interval. All right, but there are other situations where we, based on the problem that we're trying to solve, the question that we're trying to answer, we may only construct either a lower confidence limit or an upper confidence limit. So it just depends on the question we're trying to answer. And so let's look at this. If what we want to do is to construct the 1 minus alpha times 100% lower confidence limit for a population mean, then that's given by this expression, x bar minus z sub alpha times the standard error of x bar. If the question calls for constructing an upper confidence limit, then we would, instead of subtracting this quantity, this margin of error, we would add that value. So x bar plus z sub alpha times the standard error of x bar. And then if we needed to construct a two-sided confidence interval, all right, then we would calculate our endpoints. The lower endpoint would be x bar minus z sub alpha over 2 times the standard error of x bar. And the upper confidence limit would be x bar plus z sub alpha over 2 times the standard error of x bar. So these are the procedures that we would use, the specific formulas and such that we would use to test hypotheses about a population mean and construct confidence intervals for a population mean when we know the population standard deviation. And the reason we would need to know the population standard deviation is because the standard error of x bar, the true value of the standard error of x bar, depends on that population value. You'll remember that under IID random sampling, sigma sub x bar, the standard error of x bar, is equal to the population standard deviation divided by the square root of the sample size. And so in order to compute the exact true value of the standard error of x bar, we would need to know the population standard deviation. Okay, but in many situations, in fact probably most situations, we're not going to know the population standard deviation. If we don't know the population mean, which would be why we would be performing hypothesis tests or constructing confidence intervals for the population mean in the first place, if we don't know that population mean, then we more than likely don't know the population standard deviation either. So suppose now that that sigma, the population standard deviation, is unknown. Since the population standard deviation is unknown, the standard error of x bar, sigma sub x bar, is unknown as well. And so we are not able to calculate z calc, right? Because the denominator in that expression for z calc is the true standard error of x bar, which in order to calculate that, we would have to know the population standard deviation. But now we're looking at this situation where we don't know that. So we can't calculate that, but we can estimate it, right? And the estimator of the standard error of x bar is denoted by sigma hat sub x bar. And so again, in this course, we're going to be, in order to denote estimates of population parameters, what we will do is use the same notation for that parameter, but put a hat on it, right? So that's what we've done here. So that signals to us that we're not talking about the true standard error of x bar because we don't know it. We are utilizing and talking about an estimate of that quantity. And the estimate for IID random sampling is given by this expression. It's the square root of sigma hat squared over n, where sigma hat squared, again for IID random sampling, is just the usual sample variance, the version with n minus 1 in the denominator. All right, and so it's the average squared deviation of the observations in the sample about the sample mean. All right, and you'll remember, you'll recall that the reason we use n minus 1 in the denominator is because that makes s squared, also denoted by sigma hat squared, that makes this estimator of the population variance an unbiased estimator of that population variance. All right, and so in other words, the mean of the sampling distribution of s squared is equal to sigma squared itself. And so that is why we use this. All right, and so while we don't know the true population standard deviation, equivalently, we don't know the population variance, we can estimate it, all right, using the sample variance. And then once we have that, we can plug that into this formula and we have an estimated value for the standard error of x bar. So if we replace the unknown standard error of x bar by its estimated value, then we get this modified test statistic, all right, with sigma hat sub x bar in the denominator. Now, that the sampling distribution of that test statistic no longer is the standard normal distribution. It's got a little bit heavier tails. It's a little bit more spread out than the standard normal. And the reason for that is because now there are two sources of variation in the formula. There are two random variables. If I go back to the previous slide, if we look at zcalc for a moment, there's only one random variable involved in this test statistic, namely x bar. Right? The denominator is a constant; it's fixed constant. But now in this situation, we have two random variables. We have x bar upstairs, and we have sigma hat sub x bar downstairs. And both of those are random variables. And so the result of that is that this expression no longer has a standard normal distribution. In particular, it has what's known as a student's t-distribution, and in particular, a t-distribution with n-1 degrees of freedom. All right, and again, if we were to look at a graph of the sampling distribution of this expression, of this test statistic, and all we had was a graph of that sampling distribution, it would probably look to us like a normal distribution. In fact, it would look like a standard normal. But if you were to have on the graph also a standard normal curve, you would see that the sampling distribution of t-calc is a little bit more dispersed, and we need that. We need to take that into account because remember, this is the quantity that we're going to be using to make inferences, to draw conclusions, and to do that in a valid way, and in an accurate way, we have to get the best information we can about the sampling distribution of this test statistic, and that information is that it's no longer standard normal, but it has a t-distribution with n-1 degrees of freedom. And so knowing that, that provides the basis for the development of hypothesis tests and confidence intervals for the population mean mu when the population standard deviation is unknown. All right, and so this is what we need to know in order to modify the procedure that we looked at previously. All right, and so you'll see that when the population standard deviation is known, we still have available to us the three types of hypothesis tests that we can perform to answer questions about the population mean. All right. The place where we have to make adjustments is number one, in how we calculate the test statistic, which we really already discussed, and then also in determining the rejection criteria. All right. So let's take a look. So again, the formula for the test statistic in this case will be equal to the sample mean minus the hypothesized value of the mean divided by the estimated standard error of x bar. All right, and we're no longer going to call this zcalc because that would kind of indicate to us that we're going to go to the standard normal table to get the critical points. But in this case, that's not the appropriate distribution that the t-distribution is, and so we're going to call this t-calc instead to help us remember that the t-distribution is the reference distribution for this scenario. Now, the interpretation of this is that t-calc is the number of estimated standard errors that x bar is from the hypothesized value of the population mean u sub 0. So zcalc, if we remember back, that was the number of true standard errors that x bar is from the hypothesized value of the mean. T-calc is the number of estimated standard errors that x bar is from the hypothesized value of the population mean. All right, so in order to use t-calc to make inferences about the population mean, to draw conclusions for these hypotheses, we need to understand the sampling distribution of t-calc. And we've already stated that when the null hypothesis is true, then t-calc has students' t-distribution with n-1 degrees of freedom. Now, let me just issue a caveat here that this statement is exact if the underlying population is normally distributed. If we're sampling from a normal distribution or a normally distributed population, then the sampling distribution of t-calc is exactly students' t-distribution with n-1 degrees of freedom. But if the sampled population is not normal, is not normally distributed, then this statement is approximately true. So if we're sampling from a non-normal distribution, then but as long as the sample size is sufficiently large, and again, that's a ballpark around 30 or more, then the sampling distribution of t-calc is approximately students t. All right, so we just need to understand that. Okay, so given that information, that the sampling distribution of t-calc is either exactly t or approximately t, we go to the t-distribution, the t-table, to obtain the critical points for the tests. And so if we are performing the right-tailed test, then we're going to reject if our test statistic t-calc is either really small or if it's really big. And how small does it have to be? Well, if it's less than negative t, so this, let me just say here that I don't want to read the subscripts and all this, but these are the critical points obtained from the t-table. And in general, t with a subscript of k comma alpha is the upper alpha percentage point of the t-distribution with k degrees of freedom. Okay, and so the rejection criteria looks similar to what they did for the z-test. However, again, we're getting our critical points from the t-table. So for the two-tailed test, we're going to reject if t-calc is either really small or really big. All right, and those are the thresholds or the critical points. If we're performing the left-tailed test, then we're going to reject the null hypothesis for small values of t-calc. And then if we are performing the right-tailed test, then we're going to reject the null hypothesis for large values of t-calc. All right, and again, notice that if we're performing the two-tailed test, then we take the significance level, which is alpha, and we divide that by 2, and we put half of that significance level in the left tail of the reference distribution and half in the right tail in getting our critical points. On the other hand, if we are performing either a left-tailed test or a right-tailed test, right, those are both one-tailed tests, and so we put all of that significance level in the appropriate tail in order to get our critical point. All right, and then the p-value, we can also, instead of using the critical point and test statistic method, we could use the p-value method for drawing conclusions. And so these are the formulas for calculating p-values in the situation when we don't know the population standard deviation. And these look familiar. These look very similar to the formulas for the p-values for the z-test. The only difference would be now that we're dealing with a t-random variable rather than the standard normal random variable. All right, and so for the two-tailed test, the p-value is 2 times the probability that a t-random variable with n-1 degrees of freedom is greater than or equal to the absolute value of t-calc, our test statistic. If we are performing a left-tailed test, the p-value is equal to the probability that the t-random variable with n-1 degrees of freedom is less than or equal to the observed value of t-calc without taking the absolute value. And then finally, for the right-tailed test, the p-value would be the probability that the t-random variable with n-1 degrees of freedom is greater than or equal to the observed value of t-calc. So the idea is the same as in calculating the p-values. The idea is the same as it was for the z-test. Again, the only difference is we calculate these probabilities using the appropriate reference distribution. Okay, and then we can also calculate confidence limits or two-sided confidence intervals for a population mean when the population standard deviation is unknown. And so again, these formulas should look very familiar to us. All right, we're using the same kind of approach as we did for the z intervals. The only difference now is that the interval coefficient, well, there are two differences. The interval coefficient comes from the from the t-table, the t-distribution with n-1 degrees of freedom, right? And also, instead of using the true standard error of x bar, because we don't know that, we have to use the estimated standard error of x bar. All right, but other than that, the forms of these confidence intervals and confidence limits look very much like they did. Really, it's the same form, it's just the details in the interval coefficient and the fact that we're using an estimated standard error. Okay, now let's consider some approximate hypothesis tests and confidence limits for a single population mean when the population standard deviation is unknown. And so what I want you to note is that as the number of degrees of freedom increases for the t-distribution, the percentage points from the t-table get closer and closer to the corresponding percentage points from the standard normal distribution. And so if we bring up the t-table, let's look and see what happens to the values in these columns as the number of degrees of freedom increases. All right, and so for example, the upper 0.05 percentage point of a standard normal random variable, you'll recall, is 1.645, right? The upper fifth percentage point of a standard normal distribution is 1.645. Now, what happens? Let's look at the values, the t values. These are the upper fifth percentage points for a t random variable for the corresponding degrees of freedom. And so you can see that if you've got only 1 degree of freedom, the upper fifth percentage point of that t distribution is 6.314. So it's way out there. If you've got 2 degrees of freedom, then the upper fifth percentage point for the t distribution with that many degrees of freedom is 2.920. And you can see here that as you increase the number of degrees of freedom, the upper fifth percentage point of the t distribution with those degrees of freedom is decreasing. All right, let me just scroll on down here. All right, I've got these listed up to 200 degrees of freedom, and you can see here that the upper fifth percentage point of the t distribution with 200 degrees of freedom is 1.653. Well, that's pretty close to 1.645. What we would find is that if we keep going, that asymptotically, this is the values in this column are going to converge to 1.645. All right, but even with samples as of the size 200, it's getting pretty close to that. Now let's look at this column here, the upper 2.5 percentage point of a t distribution with associated degrees of freedom for each row. You can see that if you've got 1 degree of freedom, then the upper 2.5 percentage point for that t distribution is 12.706. Again, way out there in that right tail. But as you increase the number of degrees of freedom, you can see that the numbers drop off very quickly at first, and then the rate of decrease slows down, but it does continue to go. And now just let me point out that the upper 2.5 percentage point of a standard normal distribution is 1.96. And we can see that as we increase the number of degrees of freedom, the upper 2.5 percentage point of the t distribution is approaching 1.96. With 200 degrees of freedom, it's 1.972. So this is the basis for what we're saying here, that as the number of degrees of freedom increases, the percentage points from the t-table get closer and closer to the corresponding percentage points from the standard normal table. Now, what this means, the implication here is that for sufficiently large samples, approximate tests and confidence intervals can be obtained by using percentage points from the standard normal table instead of the t-table. All right, and so you might say, well, look, we spend all this time in our statistics classes learning about the t-distribution, all right, and being told that we need to use the t-table instead of the standard normal table. But the reality is, in many situations, especially if you've got large samples, then using an approximate approach is going to be just fine. All right, and so with this idea in mind, a commonly used approximate 5% significance level is given by the following. So for example, let's look at, and we're specifically talking here about a two-sided test, a two-tailed test, all right? And so again, the null hypothesis being that the mean of the population is equal to some specified value, against the alternative hypothesis that the mean is not equal to that value. And so in many cases, a two-tailed test is going to be appropriate. And for many of the examples in this particular course, this sampling course, we might be considering this kind of hypothesis. And so if that is the case, then a commonly used approximation, right, is to use -2 and +2 as the critical points. All right, so we would still calculate the t-calc test statistic, right? We have to, because we have to use an estimated value, an estimate of the standard error of X bar. But instead of going to the t-table, we might, just to kind of keep things simple and all that, we could use 2 as the critical point. If we go back to the t-table, we can see here, and this is the column that we would focus on, that once we get 20 to 30 observations, and beyond, then the critical point is about 2 anyway. And if we get beyond 60 or 61 observations, then the critical point would be a little bit less than 2. And so by using 2, we would actually have a conservative test in that case. All right. So this is a perfectly reasonable and acceptable approximation in many situations, and we're going to be taking advantage of this and utilizing this in the course. We can also use that approximation in coming up with confidence limits, and so constructing an approximate 95% confidence interval would be given by this formula. The sample mean X bar is our starting point, and then we go 2 estimated standard errors to the left of X bar to get the lower endpoint, and 2 estimated standard errors to the right of X bar to get the upper confidence limit. Okay, and so the margin of error for this interval, 2 times the estimated standard error of X bar, is a reasonable approximation, easily calculated. And again, we're going to be using this kind of approximation quite a bit in this course. And let me also say that one other reason why this is acceptable is that in this course we are going to be sampling from finite populations. Well, a finite population cannot be normally distributed. All right, a normal distribution is an infinite population. There are an infinite number of values that the observations can take on. All right, and there are an infinite number of observations or the values in that support or sample space for that distribution. But in many real-world situations, in fact most, the populations are actually finite. They're not infinite. Okay, and so we know that right off the bat we're not sampling from a normal distribution if that's the case. If the population is finite, then it cannot be normally distributed. It might be fairly symmetric and unimodal, but it's not exactly normally distributed. So from the start, in that kind of a situation, everything we do would be an approximation anyway. And so we know that if the population is not normally distributed, then t-calc is not exactly students t, but approximately students t. And so if that's the case, then insisting on using these very specific values would be maybe a little bit silly. And so this is a very reasonable approximation that we're going to be using in this course. Now, as should be clear, the hypothesis testing and confidence interval estimation procedures that we discussed thus far depend heavily on the form of the standard error of X bar and also of its estimator. So as stated previously, the expression for the standard error of X bar under IID random sampling, that is independent and identically distributed random sampling, the correct form for the standard error of X bar is given by sigma, the population standard deviation, over the square root of the sample size. So that's the true expression the accurate expression for the standard error of x bar under IID random sampling. Now, in other words, when sampling from either an infinite population or when sampling from a finite population with replacement, all right? And then based on the form or this expression for the true standard error of x bar, we can estimate that standard error by plugging in an estimator for the population standard deviation. However, if we are sampling from a finite population without replacement, then the standard error of the sample mean, sigma sub x bar, is no longer given by that expression. If we're sampling from a finite population without replacement, this is not the formula for the standard error of x bar. Hence, hypothesis tests and confidence intervals based on that expression for sigma sub x bar will no longer be valid, they'll no longer be accurate under such a sampling framework. Now, as will be discovered throughout the rest of the course, the actual expression for the standard error of x bar and the form of its estimator depend on the way in which the population is sampled, and there are many ways that a population can be sampled, all right, based on statistical efficiencies, based on logistics, and things like that. There are all sorts of reasons why populations are sampled in different ways. In order to perform valid inference about a population mean, then we need to know the form of the standard error of x bar and of its estimator sigma hat sub x bar. And these forms will depend on the sampling procedure used. So again, in your first methods class, you only considered one type of sampling procedure, and that is IID random sampling. It was probably not really made much of a big deal about, all right? It was just that was the procedure, or that was the sampling procedure that was assumed in all of the procedures that you would have been exposed to. But as we're going to find out in this course, and it's really the purpose of this course, is to learn about the different types of sampling procedures that one can use in sampling a population, the reasons for the different kind of sampling techniques, and the ramifications and the implications that the different types of sampling have on how the data must be analyzed. Remember, we want to perform valid inference, and to perform valid inference, we have to take into account the manner in which the population is sampled. All right, so let's now continue on and look at inference procedures for a population proportion. And the sampling framework is described here. So suppose that we have a binomial random experiment with n trials, each with success probability p, and that the random variable x is counting the number of successes in the sample. Then the random variable x has a binomial distribution with n trials and success probability p. And we would represent this in this way. So the random variable x is distributed according to a binomial distribution with n trials and success probability p. Now you'll recall that the mean and the variance of the binomial distribution with n trials and success probability p are given by n times p and n times p times 1 minus p, respectively. In other words, the expected value, or the mean of the distribution of x, is n times p, and the variance of x is n times p times 1 minus p. All right? Now, the proportion of successes in the sample will be denoted by p hat, and it's equal to x over n, x being the number of successes in the sample, and n the sample size. And so this is the proportion of successes in the sample. And it turns out that this is an unbiased estimator of p, the binomial proportion or probability, and so we're going to denote this sample proportion by p hat. The sample proportion is a statistic, obviously. It's a random variable that is computed from the sample, And because of that, it has a probability distribution, and we call its probability distribution its sampling distribution. Now, we will denote the mean of the sampling distribution of p hat using this notation, mu sub p hat, so the mean of the sampling distribution of p hat. And we will also, in some cases, denote it using this notation, the expectation operator, so the expected value of p hat. And so, like I said just a few moments ago, it can be shown that the mean of the sampling distribution of p hat, also called the expected value of p hat, is the underlying binomial proportion. And so that would imply then that the sample proportion p hat is an unbiased estimator of the population proportion p. We will denote the variance of the sampling distribution of p hat by sigma squared sub p hat, and also by var of p hat. And it can be shown that the variance of the sampling distribution of p hat is equal to p times 1 minus p over n. Now, the standard error of p hat is going to be the square root of its variance, and so we'll denote it either by sigma sub p hat or by SD for standard deviation of p hat, and it's given by the square root of its variance, all right? And so the square root of p times 1 minus p over n, that is the standard deviation of the sampling distribution of p hat. Now, by the central limit theorem, when the number of trials, n, is sufficiently large, then the binomial distribution can be approximated by the normal distribution. All right, so you would have covered that in your first methods class. It was called the normal approximation to the binomial. All right, and so we're going to be taking advantage of that in deriving procedures for testing hypotheses about a population proportion. So it follows that the sampling distribution of the sample proportion p hat can also be approximated by the normal distribution, all right? And in particular, for sufficiently large samples, p hat will be approximately normally distributed with a mean equal to mu sub p hat, which again is p, and a standard and a variance of sigma squared sub p hat, which was identified on the previous slide here, okay? And so it follows that if we standardize p hat, then the standardized version would have, not exactly, but approximately, a standard normal distribution. Now, one problem with using this quantity here is that the denominator, which is the true standard error of p hat, depends on p itself, right? So if we go back 2 slides, the standard error of p hat is the square root of p times 1 minus p over n. And in order to calculate that, we would have to know p. But if we're testing hypotheses about p, or if we are constructing confidence intervals for p, we're doing that because we don't know what p is. And so we would not be able to calculate the true standard error of p hat in situations where we are making inferences about p. And so we would need to use an estimated value of that. So to get around this problem, an estimator of sigma sub p hat can be obtained by substituting the estimator p hat for the unknown p in the expression for the standard error of p hat. And so if we do that, then we get the estimated standard error of p hat being the square root of p hat times 1 minus p hat over n. And from that, it also follows that for sufficiently large sample sizes, then that quantity as well will be approximately standard normal. And this provides the basis for hypothesis testing and confidence interval estimation procedures for making inferences about a population proportion p when the samples are sufficiently large. So the procedures that we're going to be looking at are called large sample procedures, all right, because they are based on this approximation to the sampling distribution of the standardized version of p hat. All right, so in testing hypotheses about a population proportion, we have the same three types of tests that we had for testing means. We have a two-tailed test, a left-tailed test, and a right-tailed test. The two-tailed test has a null hypothesis that says that the proportion p is equal to some hypothesized value against the alternative hypothesis that says that p is not equal to that value. The left-tailed test has as a null hypothesis the null hypothesis that the population proportion is greater than or equal to some specified value against the alternative that says that p is less than that value. And then finally, a right-tailed test has the null hypothesis that says that p is less than or equal to a specified value against the alternative that says that p is greater than that value. And so again, the type of hypothesis test that you would use depends on the question to be answered. The formula for the test statistic is given by p hat minus the sample proportion p hat minus the hypothesized value. And then in the denominator, we're going to use what the standard error of z-calc would be if the null hypothesis is in fact, it's the standard error would be of p hat if the null hypothesis is true. If the null hypothesis is true, then the standard error of p hat would be p0 times 1 minus p0 over n, and that's under the square root, okay? And the sampling distribution of z-calc under the conditions of the null hypothesis is that would be approximately the standard normal distribution, okay? And then the rejection criteria are the same form. In fact, it's exactly the same as the rejection criteria for the z-test, all right, because the critical points come from the standard normal table. All right, and then the p-value calculations, the p-value formulas, are also exactly the same as they were for the z-test, again, because the standard normal distribution is the reference distribution for this large sample test. All right, and then finally, we can construct confidence intervals for a population proportion. If you wanted to construct a lower confidence limit alone, then this would be the formula, p hat minus z sub alpha times the estimated standard error of p hat. If you wanted an upper confidence limit alone, then instead of subtracting, you would add, so p hat plus z sub alpha times the estimated standard error of p hat. And then finally, if you wanted a two-sided confidence interval, then you would obtain the endpoints of the confidence interval using these formulas here. So those are the procedures that you would have learned in your first methods class. The notation may be slightly different, but perhaps not, but it could be. But I'm modifying it a little bit to be helpful for the remainder of this course. So remember that these formulas, these specific procedures that we've looked at here are what you would have covered in your first methods course, and that these specific formulas and so forth, and in particular, the formulas for the standard error of the statistic we're using, whether it be x bar or p hat, the form of the standard error and the estimated expression, the estimate of the standard error, that depends, or these are the appropriate formulas if and only if we're using IID random sampling, independent and identically distributed random sampling. And again, that would be the case in two situations. If we're sampling from an infinite population, or if we're sampling from a finite population with replacement. All right? Now, if we are sampling from a finite population without replacement, then these procedures need to be modified, okay, because they do not take into account the fact that we would be sampling without replacement from a finite population. And so we need to, in order to understand the differences, we really need to understand what the procedures are under IID random sampling, and then we'll generalize and modify from there. So that is the end of this particular lecture video and this review of inference procedures for a population mean and for a population proportion under IID random sampling. We'll look at a few more topics in this module on IID random sampling just to make sure that we understand some of these other concepts that we'll be covering.